Hello again. This is Roger Koch Barr for the Bioelectricity course. We're in week number 5, where we're laying track, and we are at lecture segment number 9. Segment 9 is about determining the transmembrane current. And you are thinking, finally, this guy is going to work on the transmembrane current. Because you remember, we started this week with the equation that said Im equals IC plus I ion. And we said, to use this equation, we need to have Im. And I promised you back in the beginning that if you wanted to know Im, the way to find it was from the neighbors. Well, after all these multitude of preliminaries, we're finally talking about the transmembrane current. It's just wonderful. This is a simple argument, but let me take it step by step. We showed in the last segment that the axial current, II1, could be found from Vm1 and Vm2. This equation was our result. That's saying that we can find this current right here, which I'll denote with the blue arrow, II1. Now, if we did that for that segment, we can do it again for another segment. So I can have another expression for the current in the next segment, II2. And II2 is all the same things, just with Vm2 and Vm3 instead of Vm1 and Vm2. It's just shifted over by one segment. Here's the thing. We know that in electricity, current is conserved. If it goes one place, it has to keep on going. It's not created at any one place, nor is it destroyed. So conservation of current, sometimes called Kirchhoff's law, requires that the membrane current at site 2, this current right here, Im2, it has to be the current that's coming in, this current in blue, minus the current that's going out, this current in green, and the difference has to go across the membrane, and here it is as membrane current at site number 2. If you want to think about it this way, suppose a big current, suppose I1 is a big current, suppose I2 is a tiny current. So a lot of current is pouring in along the axis to site number 2. But it can't go on down the axis because the intracellular current that's continuing on is just tiny. So it has to be forced out. And it is forced out, and that particular current that is forced out from the inside to the outside, we call that Im2. The same thing is true, of course, in the other direction. If I1 is tiny, II2 is big, then Im2 has to also be the difference, but this time it'll be a negative value because it'll be coming inside. If you do this mathematically, these same steps mathematically, then we get this equation that's on the left, Im2. Now I'm just subtracting 1 and 2. I take equation 1, I subtract equation 2, and this is what I get, simply by subtraction of 2 from 1. And that difference then is this 3-term series, Vm1 minus 2 times Vm2 plus Vm3. An amazingly complicated expression, often inscrutable when you just see it written out there all by itself, but coming from such a simple origin. So now we have the units question again. Let's talk about it just for a minute. As before, the current is in amperes. This is in volts. This is in ohms. And everything is okay. As before, oftentimes this is in millivolts. This is in kiloohms. So this will be in nanoamperes. That's okay too. But we do have a little problem here. The problem is that in the equation that we really cared about, the one that started us on this path, the units for the membrane current were not amperes, but instead they were amperes per meter square, or some other scaled variant of that, maybe nanoamperes per centimeter square. But in any event, they were a per unit area units that were used in our motivating equation. We want to be able to use our results. We want to be able to use this result in this equation. So we're going to have some kind of a units conversion. Now you could say you should start by spelling conversion correctly. But I won't. I'll just go on to the next slide. We can get to the units we want simply by doing a division of the current that we found by the surface area through which it flows. So the way we do that is take our expression, divide by the surface area. Here it is right there. That's the surface area of an individual segment. The surface area, not the cross-sectional area. So that will be equal to 2 pi a times delta x, surface area. If we take our original expression, equation 1, divide it by the surface area, 2, then we wind up with equation number 3. It's a little bit confusing looking, but notice this. In the limit, as delta x grows small, we have Im equals 1 over 2 pi a d squared Vm dx squared, where all of it is evaluated at the point of interest. So if this is Im2, it'll be this derivative evaluated at site number 2. If this is Im3 or 4 or 7, the derivative on the right will likely be evaluated in the same way. So if you discretize the fiber, when you discretize the fiber, the result you get is this result. This is usually the result that you want if you're doing a numerical calculation. If, on the other hand, you're thinking of the problem mathematically, or looking in a reference book that shows the result mathematically, or lots of times just in discussions of the problem, you get this result that says Im goes as 1 over 2 pi a times d squared Vm dx squared. Now you're thinking, what is this partial derivative sign that this guy snuck in on me? It's just done that way to say that it's the second derivative in space, even if things are changing in time. So we have it. We've done it. Hooray! We have gotten the transmembrane current, and we got it from the neighbors, and it is the second derivative. That's thought-provoking. The transmembrane current is not proportional to the transmembrane voltage. It's not proportional to the slope of the transmembrane voltage. It's proportional to the second spatial derivative of the transmembrane voltage. You're going down the track and you're looking for the bumps, because the bumps are where there are those big second derivatives. And where there's a bump in the track, that's where there's a membrane current in the fiber. In the figure here of the Duke University dorms, they're interesting because of the bumps. I mean, yes, there is a wall, and yes, there are straight lines on the wall, but it's the bumps here, the bumps here, the irregularities there. That's what makes the architecture interesting, as is the case for all Gothic architecture. And in our track, it's the bumps that get your attention if you're on the train. And in our fiber, it's the bumps that get your attention as far as membrane current. Thank you for watching. We'll come back and look at this another way in the next segment.